All right, the fifth main type of chemical reaction is called combustion. And this is a chemical change where you have an element or a compound that's going to react with oxygen. And most time it's going to produce energy. A lot of the times that's going to be heat, but light can also be produced. One of your reactants is always going to be oxygen. So we're always going to see oxygen on our reactant side, keeping in mind that oxygen is a diatomic molecule, so you'd want to write that as O2. And the other reactant is normally going to be a hydrocarbon, and a hydrocarbon has hydrogen and carbon in it. You will see sometimes that you'll have a mixture of hydrogen, carbon, and sometimes an oxygen might be in there, but mainly it's hydrogen and carbon. And your products will always be carbon dioxide and water when you have a hydrocarbon involved. Some of the main hydrocarbons, you probably have heard of methane, CH4, propane. Butane is another one. So notice they're all hydrocarbons. We have carbon and hydrogen. You will see some that you might have, carbon, hydrogen. You might have an oxygen in there as well. So if that happens, don't be surprised or think that there's something not right. That's okay. Here's an example of a combustion reaction. This doesn't involve a hydrocarbon, but it is reacting with oxygen. So because of that, it is a combustion reaction. It's also an example of a combination reaction because you can see that you have two elements that are being combined together into one product. So we mentioned a while ago that there are some equations that can fit into more than one category, and this is an example of that. So let's do a practice problem here. We're going to mainly be sticking with hydrocarbons though for our practice problems and for what you're going to see on quizzes and tests. For this one we want to complete the reaction, and we also want to balance it when it says to complete it. So we are going to have C6H6, and we know that a combustion reaction is always going to involve oxygen. So we're going to add O2. Remember, it's diatomic. And then earlier it said that your products are always going to be, if you have a hydrocarbon, water and carbon dioxide. So I'm going to add water and carbon dioxide. Now that would be a good type of skeleton equation, but we don't have, it's definitely not balanced yet. So I'm going to go ahead and if you want to do the reactants and products and do the T-chart thing, you definitely can. We have carbon, hydrogen, and oxygen here, and some of these combustion reactions can be a little tricky to balance. So I want to just give you a little bit of advice. You should always start first with carbon. I'd always balance carbon first, and then second I would go through and balance hydrogen. Always save your oxygen for last. Okay, do it third. So if I go through here just to get us started, we have 6 carbons on the reactant side, 6 hydrogens, and only 2 oxygens. And then on the product side, I have 1 carbon, I have 2 hydrogens, and the reason that we're saving oxygen for last is I want you to notice that oxygen is part of water and is part of carbon dioxide. So we have to add the oxygens together, and in this case you have 1 from water and 2 from carbon dioxide, so you're at 3. So because you have an odd-even situation, sometimes it's good to save that one for last. Sometimes it'll solve itself. So if we start with carbon, we have 6 of those, so we'll have to put a 6 in front of our carbon dioxide, so that takes care of carbon, and it also increases our oxygens now to 6 times 2, which is 12, plus the 1 that we still have from water, so now we're at 13 oxygens. If we do hydrogen second, we have 6 hydrogens here, and so that means if we would have put a 3 out in front of our water, we would have 6 hydrogens, and it also increases our oxygens. We still have our 6 times 2, we have our 12 here from carbon dioxide, and we have 3 now from water, so we're at 15 total oxygens. So if we come back over here then to our reactant side where we only have 2, this is the side that we need to bring up higher to meet the 15 on the other side. There is nothing that you can, no whole number that you can put in front of oxygen that's going to give you 15. And so I want to suggest temporarily that we go with 7.5. Now we're not going to be able to leave it as 7.5, but temporarily we want to at least get to the 15 oxygens there. So if we were allowed to keep fractions, that would be okay, but our coefficients do need to be whole numbers. So what we're going to do in order to get rid of that 7.5, we're actually going to have to take the coefficient in front of each and every one of our substances, and we're going to have to multiply it by 2. So right now we have a 1 in front of our C6H6, and so 1 times 2 is 2. And we have 7.5, so 7.5 times 2 is 15. So we'll put a 15 there. And then we have 3 waters right now. That's going to change to a 6, 3 times 2. And then we have 6 carbon dioxide. 6 times 2 is 12, so we're going to want to put a 12 here with our carbon dioxide. Now you can do a check and make sure that this works. Definitely good to use pencil when you're balancing, but if you have 2 times 6, now that gives us 12 carbons, and it also gives us the 12 carbons on the product side. We have hydrogen, 2 times 6, which is 12, and we also have 6 times 2 with the water, so that gives us 12 hydrogens. And so at this point we just need to check the oxygen. So 15 times 2 gives us 30. And so if we have 30 on that side, we need 30 on our product side. Now keep in mind oxygen's in 2 places. So we have 12 times 2, so that gives us 24. And then we have the 6 times the 1. So we have 6 from the water plus the 24 from the carbon dioxide, and that gives us indeed 30. So again, the 7.5 does balance it, but we can't leave it having that fraction or decimal, so we do need to go through and multiply everything by the same amount. Notice that we still have our least coefficients need to be the least ratio possible, and 15 isn't divisible by anything the way the 2, the 6, and the 12 are. So this is still in the lowest ratio of coefficients possible. This happens with combustion reactions. I don't know, not always, but it happens frequently, so definitely something you're going to want to revisit. Maybe listen to this practice problem again, because I know you're going to have some on quizzes and tests where you are going to need to do that. We'll do one more practice problem together. Here is not quite a hydrocarbon. It does have some oxygen in it, but it still works the same way. So we're going to want to have our formic acid, HCOOH, and this is just the way that this is normally written. We're going to want to add our oxygen, and we're going to want to keep our products as carbon dioxide and water. And again, it doesn't matter which one you want to write first, as long as carbon dioxide and water are both on your product's side. So again, I would recommend that you start with your carbons, and if you want to do a T-chart, you're more than welcome to. I'm not going to for this one. But you have 1 carbon here on the reactants and 1 carbon on the products, so your carbons are already balanced. And then hydrogen should be the next one that you do, so you have 2 hydrogens here on your reactant side. You also have 2 already on the product side, so hydrogen is good. And so we just need to worry about oxygen. So here we have 1, 2 oxygens from the formic acid. We also have 2 from the oxygen molecules, so we have 4. And here we have 2 oxygens, and from the carbon dioxide we only have 1 from the water, so we're at 3. Now maybe you would be worried thinking, oh my goodness, we have another odd-even situation, but this one we can solve a little differently, because we can put a number out in front of water that would give us 1 more oxygen, that would bring us up to 4. So we can go ahead and put a 2 in front of our water, and by doing that, that does create the 4 oxygens that we need. So oxygen is good, but it does create some problems with the other elements. So I'm going to go ahead and erase some of these marks that I had, because we're going to need to go back and make some changes. So at this point now, oxygen is good. We have 4 on each side, but it did mess up our hydrogens, since we now have a 2 in front of H2O. So we have 4 hydrogens total. If we put a 2 out in front of our formic acid, we will again have 4 now hydrogens. So hydrogen is balanced, and we just want to balance our carbons, we have 2 carbons here, and so we'll want to put a 2 in front of our carbon dioxide here to give us the 2 carbons that we need. So by doing that, we have carbon is good, but it did change our oxygen. But don't panic, it's okay. So again, we have 2 oxygens here. We have 2 oxygens here, but we have it multiplied by 2. So we have 4 total oxygens there, and we have 2 oxygens here. So we have 6 oxygens on our reactant side. And if we take our 2 times 2, that's 4 from our carbon dioxide, and 2 oxygens on water is 6 oxygens there. So we have 6 oxygens on both sides. We have the same amount of hydrogens on each side and the same amount of carbons on both sides. So this one might have been a little tricky, just we had to go back and kind of adjust some things multiple times, but it does work out. Now this third practice problem I'm going to have you work on, and this one is very similar to practice problem number 1, only you're not going to need to go and do a lot of, you don't have to go through at the very end and multiply by anything. So this one works out nicely without needing to have a decimal or anything, but start with carbon first and then hydrogen, and then balance your oxygen last, and it will balance out pretty easily for you. To finish up combustion reactions, just as a review, this is the most common equation for combustion reactions. We normally will have a hydrocarbon, so however many carbons and hydrogens that might be, kind of changes from equation to equation, but we're always going to have oxygen and some other compound as our reactant, and our products we're always, if it's a hydrocarbon, we're always going to have the carbon dioxide and the water. And those are the ones that you're going to see the most of is the hydrocarbon examples.